Algebra 2 Honor 6.3a notes. We're going to be looking at logarithms, and logarithms are the inverse functions of exponentials. So we've been looking at exponential functions, so now we are looking at the inverse functions of exponential functions. And so the definition of, well, before we get to that, let's get this a little bit right before here. You know that 2 squared is 4 and 2 cubed is 8. However, for what value of x does 2 to that power equal 6? And so this is what we do to, we use logarithms to find this. And so this 2 to the x equals 6, we have logarithms, and logarithms have a base, and the base is going to be 2. And the output of the logarithm is going to be the exponent. So we say log base 2. It needs to be a subscript. It needs to look like a subscript. And I'm going to leave a space, equals the exponent. And the argument is what 2 to the x equals. Let's look at that again. Let's say we have 3 to the x equals 11. We would write log base 3. It needs to be a subscript. And then you're thinking if there was a straight line here, the 11 goes as what we call the argument, and then equals the exponent. The output of the logarithm is the exponent. And so the definition of logarithm can be generalized as follows. Let b and y be positive real numbers with b not equaling 1. Then the logarithm of y with base b is denoted like this. So this is said log base b of y, which is right here, log base b of y. And log base b of y equals x. Remember, the output of a logarithm is the exponent, and your base is b. So we get b to that exponent, and what that equals was the argument of the logarithm. You're going to have to be able to go back and forth between these two forms. And so this form is the exponential form, and this form is the logarithmic form. And they are inverse functions. And so you're going to be given logarithms, and you're going to need to write. And the base here is 6, and remember the output is the exponent. And so the base is 6, the exponent is 3, and what that equals is the argument of that logarithm. And so I had this saying, only in class I usually demonstrate it. Lean to the left, lean to the right, equals the middle, get it right. Lean to the left is the base. Lean to the right is the exponent, and then equals in the middle, 216, get it right. Lean to the left, lean to the right, equals the middle, get it right. That's something I usually do in class. Another thing that people do is swoop, there it is, and they start swoop to here it is. So it's 6 to the third equals 216. All right, so part B, the base is 7. And remember, the output of a logarithm is the exponent. And then the argument of the logarithm is what that equals. 7 to the 0th equals 1. Again, I would say lean to the left, lean to the right, equals the middle, get it right. Lean to the left, lean to the right, equals the middle, get it right. Or other people do the swoop, there it is. And so start with the 7. That's the exponent. Oops, doesn't like that. That's the exponent, and then the end result is 1. So there's some different things to use, but you're going to need to be able to go back and forth because you're going to need to be able to do this abstractly. Instead of just going, I know 6 cubed is 216, or I know 7 to the 0th is 1, you might have something that's a little more abstract. And so then you need to understand that the base is a, the output of the logarithm is the exponent, and this argument of the logarithm is what that base to the exponent equals. All right, so in part C, the base is 21, the exponent is 1, and then equals the argument. So that's what we want for writing it in exponential form. By the way, on your homework, be sure to write down the original problem. All right, in part D, the base just has to be positive and it can't be 1, and so having a base of 1/5 is okay, but then put that in parentheses, and that 1/5 is raised to the exponent. Remember, the output of the logarithm is an exponent, and then that equals the argument of the exponent. Lean to the left, lean to the right, equals the middle, get it right. And you should understand that 1/5 to the -1 is 5, that those are equal. All right, so rewrite those in exponential form. Those are your answers. Be sure to show the exponents, and that's it. Now, just notice that this log base 7 of 1 equaling 0, anytime that this argument is 1, it makes sense that the exponent is 0, because if log base b of 1 equals 0, because b to the 0th, the base raised to an exponent of 0, will always equal 1. That's going to be a property of logarithms you're going to want to know. So when the argument is 1, the output's going to be 0. And then in part C, we had log base 21 of 21 equals 1. That's how we say that. Log base 21 of 21 equals 1. And when these match, we should expect that the output is 1 because of the fact that 21, right, to the, lean to the left, lean to the right, equals the middle, get it right, 20, the base to the first power is always itself. So when this base matches the argument, we should expect that the output is 1. And that's what this is saying right here. Log base b of b equals 1 because b to the first is b. Those are properties of logarithms. We will be generalizing them and just say log base, say a, of 1 equals what? Well, because the argument is 1, we should know that the answer is 0. Or if I have log base a of a, since the base is a and the argument is 1, a to what power is itself? You should know that that output is 1. So in example 1, we rewrote equations that were logarithms into exponential form. Well, we need to be able to go backwards. Rewrite equation in example 2 in logarithmic form. And you need to make sure that the base is a subscript and it looks like it's a subscript. Again, make sure you copy down the original problem in your homework. So we're going to have log, the base is 9, so that goes down here. You want to kind of think there's this imaginary line, leaving space for the argument, and the exponent is 2. The output of the logarithm is the exponent. And what the base to that exponent equals is the argument of the log. So we aren't going to actually draw in that line, but you need to make sure that you structure it correctly. So log base 9 of 81 is 2 because 9 squared is 81. In part B, log, what am I going to write as that subscript for the base? Well, the base is 20. And then I leave space, and what the log equals is the exponent, and 20 to the negative 1 is 0.05, so that becomes my argument of the logarithm. Part C, log base, the base is 16, make sure it is a subscript, leave space, and the output of the logarithm is the exponent that you raise the base to get 8. And the argument of the logarithm is the value of 8. Part D then, we get log, the base is 15, and we could put, so again, I'm thinking of that kind of line there, and I'm gonna, so, and then that will equal the exponent of negative 2. So that's rewriting it in logarithmic form. So in example 3, evaluate this. When you see part A, you need to think that 4 to what? This is not calculator. No calculator. 4 to what power equals 256? If I think of this as a variable, we're answering 4 to what power is 256? And the answer to that, well, 16 squared is 256. And so that is 4 to the 4th. And so 4 to the 4th will be 256. On this next one, we're asking 8 to what power is 0.125? Well, you need to know, this is a decimal value you should know. You should be able to know that 0.125 is 1/8. So 8 to what power is 1/8? Well, it's a negative 1, right? 8 to what power is 1/8? Well, that means x is negative 1. The next one, 1/3 to what power is 27? 1/3 to what power is 27? Well, if I make this 3 to the opposite of x, I'm going to get 3 to what power is going to be 27, and it is 3 cubed is 27. And so that x is going to be negative 3. You need to make it negative so that the fraction flips, and then 3 cubed is 27. And then this next one, 64 to what power is 8. Well, the square root of 64 is 8. So x must be 1/2. So the answer to this is 1/2. These are not calculator problems. Do not use a calculator on these. Figure them out using mental math and the concepts of exponents and bases. All right, then we're going to get to a section that is calculator. And we have a couple of special logarithm bases. And we have that, and a common logarithm is a base of 10. And it's denoted log base 10, but since we use it enough, log base 10 gets just plain log. So if you see log base 10 or log of x, that log of x, the base is understood to be 10, and that is called the common logarithm. But then we have the natural logarithm, and its base is e. We've seen e, it's 2.7 something about. It's a number between 2 and 3. And it means this, log base e, and then you have your argument equals the exponent, but we do not write it log base e like that. We get a special notation, and it's not in, it's ln. And so this right here, that is not a I or a 1, it's an L. And natural logarithm, when I know the base is e, we write it like this. And when you move up in math, that's what we go to. That's our go-to, is use natural logarithms with a base of e. So you will see in your calculator log and natural log, ln. And so we're going to go to evaluating these. And so in part A, that's a base 10. Because it's log, it doesn't show a base. It's understood to be 10. And so I hope I have my Desmos graphing calculator here. Yep. Get rid of all of that. And so I'm going to go to functions. And you'll notice towards the right, we have an log. So we have log. And we're evaluating log of mean 21, right parenthesis. And we're going to go to 3 decimal places. So 1.322. It's approximately. So use squiggle equals approximately equal to, and round to 3 decimal places. And in part B, this is your natural log because it has a base of e. So we're going to go to calculator. And if I go to functions, natural log, you can see the ln there. And we want it evaluated at 0.54. And that's negative 0.616 to 3 decimal places, negative 0.616. Sometimes I like to put the 0 in front just to kind of accent where the decimal place is. And that is a calculator problem. But all the rest of these were no calculator. That's it.